In this question, I want to talk about how we can query across multiple tables. I want to talk about joins. We've looked at single table operations that I can perform, where I'm performing an operation on one row at a time, or I'm performing an operation on a grouped, non-overlapping, exhaustive partitioning of the data with a group by. Let's take a look at what we can do if we want to look at two or more tables at the same time. And part of our motivation here, and a motivation that we will see when we talk about all of the advanced functionality in SQL, is SQL is really different than your programming languages. And one thing that makes it so different is there's no variables. Like in a programming language, you'd say, of course there's variables. What else? How could you write a program without a variable? In SQL, there's things that kind of look like variables, like at my Postgres runner, I have things that look like this. And you can see it seems to be setting a variable to 1, 2, 3 and then selecting that variable. And I can even do things like set a string and say select where the name equals that string, but that fails. It seems to be the case that I have to set this with like extra quotes. Well, what I can see here is this is not really a variable. This is just some sort of textual substitution that's being done at the level of my query runner. It's not really a database level variable. One thing that I can identify that makes this very distinct from a database level variable is you can see that I can actually use this to parameterize what table I search from. This is really just a textual inclusion because in general, this is not possible in SQL, as we will see when we talk about dynamic SQL. With that said, let's return to our data, which consists of something new. We have weekly data here, and this weekly data, let's talk about why it is difficult in SQL for us to perform operations on more than one row at a time. Here we have some weekly data that we're working with in pandas. And it is totally reasonable and very likely that we might perform some sort of group by operations in pandas where we look at the structure, at different parts of the structure, like we compute a mean, or where we look at the first row and we compute this mean divided by the very first value we saw. Because in pandas and in NumPy, the data has an explicit ordering, and that's the ordering against the index, and the data is all resident in memory, so it costs us absolutely nothing to just jump around this structure, or more or less it costs us absolutely nothing to jump around the structure. If we want to say, give me the mean divided by the very first value that I saw, that's not expensive in pandas. Whereas in SQL, if the data is on disk and we have to bring that into memory, and it's on slow spinning media disk from 1989, it is very expensive to do. This is one of the reasons why that simple select operates on one row at a time, because you can think the way that you would have implemented it naively in 1989 is you would have said, okay, figure out which pages from disk I have to read. Read one row from this page, or read the whole page, and then read one row and perform one operation, throw away that memory, and then keep doing that because it's 1989. I've got like 64 kilobytes of RAM max, and I've got a 1 megabyte database. I can't load that into memory at once. Whereas in the pandas universe, everything's in memory. So, random access is basically trivial. One of the core intuitions behind SQL is that random access is considered to be expensive. Now, let us return to our data set that we were looking at before. Our adventurers, their profession and their species, the monsters that they fight, what level they are, and how much XP and hit points each monster is, and which monsters they defeated at which time. And using this data, we will take a look at some joins. And so, just to eyeball it, this is what our data looks like. If we wanted to look at two tables at the same time, we need special syntax for this. A single, naive, simple select statement typically looks at one table at a time, or looks at one table per from clause. Generally, everything related to joins can be conceptualized very easily in terms of the Cartesian product. If I select from two tables at the same time, what I am doing is a Cartesian product of these two tables. So I'm taking every row of one table and every row of the other table. So I'm taking row 1, row 1, 2, 3, 4, 5, row 2, row 1, 2, 3, 4, 5, and so forth and so on. And if I didn't limit this, you could see that the count of the number of rows I get here is strictly the product of the number of rows in each of those individual tables. Now, if I did that, I don't know that that's particularly useful. I got every row of one table against every row of the other table, but there's interrelations between these. For example, I'm looking at the table that indicates information, like how much each monster was worth in terms of hit points, and which monsters were vanquished by which adventurers. Well, I don't really care about how many hit points or how many experience points the Balrog is worth when I'm thinking about when this adventurer killed a dragon. I really want to match like to like. And what I can do is I can look at this data and I can understand that what I'm actually doing is taking two tables. I'm looking at them side by side. Here's the data from each of those tables, and I'm just computing the Cartesian product of all the tuples from one of these and all the tuples from the other. And what I can do is I can select from these only the tuples where something matches up, where the monster here matches up to the monster here. And when I do this, I don't have to print it out in this fashion. I might print it out like this, and I don't need both columns for the monster. That's always the same. This is what an inner join is all about. All of the joins are really conceptualized about computing the Cartesian product and then finding a way to subset that Cartesian product with some predicate. And here you can see a different syntax. Instead of selecting from both tables, I select from one table and I inner join, and I give the predicate that I would use in the where clause as the join on. So here you can see an inner join on this. Now, there are different types of joins that I need to work with. Inner joins, left joins, right joins, outer joins, and natural joins. The natural join is probably the easiest of these to understand. Here, let's go back to our problem with identifying magic users. Here are each of our adventurers and their profession. And we know that if we want to identify if somebody's a magic user, we could express their magic user state with a case statement. But we could think that if the number of professions, the character classes, gets very large, this is going to get really unwieldy, and this may be permanent data that we want to have stored somewhere. So what we could do is we could create a table that stores each character class and whether it's a magic user, and we could maintain that over time. And we could take our original data and join it against this table on that profession field. A natural join is a join where instead of specifying the linkages between the two tables, what you do is you say, use the column names and figure it out from the column names. And because I created these tables myself, I know one table has profession, the other table has profession. Those are the only common column names. Well, that's just a natural join. In general, I avoid using natural joins unless I immediately created the tables myself, because this can go wrong very easily if the columns happen to change names. I typically don't use a natural join. But if I create the tables myself, it's a little bit less syntax. Now, when I create this table, I might want to create this parsimoniously. I don't necessarily want to include everybody who's not a magic user. I only want to create the ones that I've thought of. And by default, if you're not in this table, you're not a magic user. And so what I could do is I could do my inner join here. But when I do my inner join, the nature of the inner join is an exact match, trying to find everything that matches on both sides of this. If there is some non-matching entities like cleric and mage, the thief and the warrior on the left-hand side that don't match to anything on the right-hand side, they will be elided. What happens with the inner join is I want every row and the intersection between the left-hand side and the right-hand side, the table I'm working with and the table I'm joining against, I want everything that matches exactly. But in this case, I actually don't want that to be the case, because then I'll accidentally fail to give me any information about the character classes I don't know anything about. So what I might do is I might change this into a left join. The left join says, give me exhaustively whatever's on the left-hand side, all the adventurers, and what you can pick up matching against the right-hand side, magic users. And so you can see I get a bunch of nulls in that is magic user for any character class I hadn't seen of before. And this is a very good place where I might say, okay, now that I've done that, now coalesce to give me a value that I'll use later, as is magic user. Similarly, if I stored who won the game. In the game of NetHack, it's who ascended to another plane of existence. And I have the winners of the game in a temporary table. And I join this table against that temporary table. Well, I might want this to be a right join. I want it to have every adventurer who I know who's ascended, even if I didn't have any information about them. Now, notice something interesting. When you're doing the inner join, it doesn't matter which side of the two tables you pick columns that overlap. In the case where I was matching profession against profession, it doesn't matter if I get a profession from the left-hand side or the right-hand side for the inner join, because I was matching on both of these existing and them being matched up. For a left join or a right join, it matters very much so which side I look at, because if I look at the side that might be null, I might be missing. I might miss out. So here I have to be very careful. I'm going to do a right join. Then if I'm going to look at a column, I probably want to look at the column on the right-hand side. Otherwise, I'll get nulls where the data actually existed. Just because the data didn't exist on the left-hand side doesn't mean it exists on the right-hand side. Or if I wanted to just not really think too hard about this, I could coalesce. So if I want to just make my life easy and just say, you know what, I'm just going to make this as easy as I can could just coalesce. But you can imagine that gets really clumsy. Now, I want to share with you one other thing, and we'll talk about this in far greater depth when we go into advanced SQL and advanced mechanisms for performing queries, but it is not uncommon for me to sometimes want to look at two rows from the same table at the same time. And this is what's called a self-join. The mechanics of it are identical to the mechanics of a normal left, right, inner, outer join. The mechanics really don't differ that much. What it is the reason for why you want to do this is its own entity. There's actually 2 or 3 interesting use cases for this, namely one-step transitions in some sort of graph data or tree data, and the other one might be if you want to get some sort of data-aware rolling behavior, like when you do a pandas.rolling and you can give it the timestamp, so you want every 30 minutes and you want some sort of overlapping data-aware rolling on non-evenly spaced data, you can actually do it with the self-join. So I just want to plant the idea of the self-join in your head. Here, I'm going to join this table against itself. And I'm going to join it against itself, matching up the adventurers and the monsters exactly. This is the table of who beat whom, or who defeated whom. And where the first monster that was defeated and the second monster defeated, well, it was somewhere between 0 seconds and 1 day. So this here gives me all of the places where each adventurer defeated the same monster within 1 day. They defeated 2 witches in 1 day, 2 ogres in 1 day, 2 beholders in 1 day, 2 elementals in 1 day, 2 medusae in 1 day. And with this, I could do something like count them. You could see this adventurer happened to defeat 2 dragons in 1 day. The other one happened to defeat 2 orcs in 1 day. Another one happened to defeat 2 witches in 1 day. I can use this to look at 2 rows at the same time, namely, or 2 or more rows at the same time in this case, namely, any rows where within the same day, or within the same 15 minutes in this case, they saw the same monster and defeated the same type of monster. And so, to wrap this up, what we looked at was inner joins, left joins, right joins. We didn't talk about outer joins too much, but it's basically, if inner join is, you got to have the same thing on both sides. Left join is, I care to have everything on the left-hand side, even if there's not things matching on the right-hand side. Right join is vice versa. Outer join is, give me everything, including things that didn't match on the left or right-hand side. It is the entirety of this, the full Cartesian product. We talked about natural joins, which come up if you want to write things a little bit simpler, but are really not that useful. And self-joins, we planted that idea in your head.